So now I've set the stage that gases move either in or out of the body based on a pressure gradient. And the two gases that we're talking about are oxygen and CO2. And they each exert pressures. So PO2 is the partial pressure or the pressure exerted by oxygen. And for CO2, it's PCO2. Now we're going to trace gas movement in the alveoli and gas movement in the cells, for instance, muscle fibers. And as we trace this gas movement, we're going to talk about how the reason for the movement is because the gases are moving from an area of higher pressure to lower pressure. So we're going to spend a lot of time on this figure, and it's really important to use this figure as you do your workbook questions to make sure you have a good understanding of this figure. So I'm going to be using numbers in this figure because there are real numbers, but what's more important than the absolute numbers is understanding where the numbers are higher and how the numbers are driving gas movement one direction or the other. And third is how these numbers change during exercise. Okay, so we start up here in the atmosphere. Okay, and you know that we got these numbers from our calculations. So in all of our examples, we are going to assume that the atmospheric pressure is standard, which is 760. And remember that the concentration of gases is constant. So if the pressure in the air is 760, okay, and we know that the concentration of oxygen is 20.93%, then we can easily calculate and determine that the partial pressure of oxygen in the atmosphere is 159.2. And along the same lines, we can calculate the partial pressure of CO2 in the atmosphere, which is 0.2. And so those are the numbers we will use for our example, but just remember that these partial pressures are going to change as the atmospheric pressure changes. But for our examples, we're going to use an atmospheric pressure of 760. All right. So up here in the atmosphere, we have a PO2 of 159.1 millimeters of mercury. That's a pressure. And we have a PCO2, a pressure exerted by CO2 of 0.2 millimeters of mercury. So there's not a lot of CO2 in the air, and therefore the pressure of CO2 in the atmosphere is relatively low compared to oxygen. Now when we inhale, we take air into our lungs, and that air ends up in the alveoli and gets mixed with the air that's already in the alveoli. And the result is that we see in the alveoli, we have an average PO2 in the alveoli is 105, and the average PCO2 in the alveoli is 40. Okay, so keep these numbers in mind, and again, the absolute numbers are not as important as understanding which one's higher and how they change in different parts of the body. So in the alveoli, we have a PO2 of 105 and a PCO2 of 40. And here we have venous blood, and here we have arterial blood. And you see that the venous blood coming in to the alveoli, all right? So this is the pulmonary vein coming into the lungs. The pulmonary vein is going to branch into the pulmonary capillaries. And so this is the blood that is going to surround the alveoli. And so if this blood has a PO2 of 40, and the PO2 in the alveoli is 105, okay, and we know that gases are going to move from high to low, okay, so PO2 is higher in the alveoli than in the veins, and therefore oxygen is going to move from high to low, and so oxygen is going to move from the alveoli into the capillaries. Okay, so it's going to go from 105 to the P1, which is the PO2 in the alveoli, is 105, and the P2, which is the PO2 in the veins, is 40, and therefore P1 minus P2 equals 105 minus 40, and therefore the pressure gradient of oxygen between the alveoli and the capillary blood, the pressure gradient is 65. So we have a driving force driving oxygen out of the alveoli into the capillaries, and that driving force is 65. Okay. Now we do the same thing for CO2. So in the alveoli we have a PCO2 of 40, and in the veins we have a PCO2 of 46. Okay, and remember P1 is always the highest. So here P1 is 46, P2 is 40. Okay, and the pressure is higher in this venous blood that's coming into the capillaries than it is in the alveoli, and therefore with CO2 we get CO2 moving from the blood into the alveoli. Okay, and the gradient is P1 minus P2, which is 46 minus 40, and so we have a gradient of 6. So the gradient for oxygen was 65. The gradient for CO2 is only 6. Okay, but there's still a gradient, and it's favoring oxygen leaving the blood, coming into the alveoli. Okay. So for now, you're just memorizing these numbers. Again, the numbers aren't as important, but you know that oxygen moves from the alveoli into the blood. You know this. Okay, and therefore you should know that the PO2 is going to be higher in the alveoli than in the blood. That's why it's moving in that direction. Okay, at the same time, you know that CO2 moves from the blood into the alveoli, so we can exhale it. So again, you should know that the PCO2 in that blood coming in from the veins that goes through the capillaries is going to be higher than the PCO2 in the alveoli. That should be obvious. Now, think about it. Think about why the gradients between that are driving these flows are so different. Okay, so the pressure gradient driving oxygen into the body is 65, but the pressure gradient drawing CO2 out of the body is only 6. Okay, so let me give you a hint of why this is. If you remember Fick's law, okay, remember what Fick said is that the factors that affect the rate of diffusion are right here. Okay, one of the factors affecting the rate is going to be the pressure gradient. Okay? And the pressure gradient for oxygen is 65, but for CO2 it's only 6. Okay? The reason for that is because remember that oxygen and CO2 have different diffusion coefficients. Okay? The diffusion coefficient for CO2 is 20 times higher than the diffusion coefficient for oxygen. Okay? Therefore, because CO2 has such a high diffusion coefficient, it doesn't need to have as high of a pressure gradient in order to get CO2 in the body. So it's a way that the body compensates and ensures efficiency. It's not going to maintain a high gradient that's not necessary. Oxygen is going to need a much higher gradient, a much higher P1 minus P2, because it has a lower diffusion coefficient. And that's the reason for these two gases having such different pressure gradients. Okay. All right, so let's move on from here. So what happens is, as the, let's get this erased. What happens is, as the blood leaves the veins, goes through the capillaries, okay, and here we have pulmonary diffusion. Okay, so we have oxygen moving into the blood, we have CO2 moving out of the blood, and then the capillary blood comes out and ends up in the pulmonary vein and goes back to the heart. Okay? And what we see is that as the blood moves through the capillaries in the alveoli, the PO2 equilibrates with what's in the alveoli. Okay? So you can see that, and the PCO2. You can see that the PCO2 is going to leave the blood, okay, until there is no more driving force, right? It comes in as 46. As CO2 leaves and leaves and leaves, it's going to drop. And once CO2 gets to 40, it will no longer drop because there's no more gradient to lose more CO2. So what we end up with is an equilibration at 40. And so what we see in arterial blood is a PCO2 of 40. Okay. All right. When we look at oxygen, okay, coming in, we have a PO2 of 40, and the PO2 is much higher in the alveoli, which is going to drive oxygen out. And so the oxygen is going to raise in the capillary until it gets to 105. Because once it comes to 105, once the PO2 in the blood is 105, you have no more gradient. And without a gradient, there isn't going to be any more oxygen coming into the blood. So what you're going to have is a PO2 in the arterial blood of 105. This drawing says 100. Change it to 105. Okay, we change this to 105. If you want to talk more about why the book says 100, we can talk about that. But at this level, you know, let's just keep it at 105. Let's just keep it simple for this first pass. So the blood that moves through the lungs is going to equilibrate with what's in the alveoli. So what we end up with in the arteries is the same PO2s that we saw in the alveoli. Okay, so we see a PO2 of 105, we see a PCO2 of 40, and then the blood goes through the pulmonary artery back to the heart, left atrium, left ventricle, out into the system, where it remains the same. Okay, we still have a PO2 of 105, we still have a PCO2 of 40. The only thing that's going to change these pressure gradients is if we gain or lose gases, and we don't gain or lose anything in the arterial system. Remember that all diffusion occurs among the tissues within the cells. So that's where we're going to see changes, is when the blood enters the capillaries that go through the cells. Okay. And remember, down here, this is pulmonary diffusion up here, and this is capillary diffusion down here. Okay. So as the blood enters the capillaries and goes through all the cells in the body, what we see is that CO2 leaves the cells and goes into the blood, and oxygen leaves the blood and goes into the cells. Okay. And so because these gases are moving in this direction, you can guess what the pressure gradients are in the cell. Okay. So if a PO2, the blood comes into the capillaries of the cells at a PO2 of 105, and you know that the gases are moving into the cells. Okay, what does it tell you about the PO2 in the cells? Okay, is the PO2 in the cell higher or lower than 105? Okay. It must be lower, okay, because if oxygen is going to move from here into here, it's because the oxygen pressure is higher in the blood. Okay, so the oxygen pressure in the blood is 105. It's not on your picture, but I'll tell you right now that the PO2 inside of the cell at rest is 40. Okay. So again, we have a gradient of 65. Okay. And that gradient is causing oxygen to leave the capillaries, go into the cells. Okay. And as before, the oxygen is going to continue to leave the capillary blood until it equilibrates. Okay. And it's going to equilibrate with what is in the cell, which is 40. Okay. So it's going to be 105. It's going to leave the blood. As it leaves the blood, it's going to drop to 100, it's going to drop to 80, it's going to drop to 70, etc. Once it drops to 40, it's going to equilibrate. We're not going to have a pressure gradient anymore. And what we're left with in the blood that comes out of the cells into the veins is a PO2 of 40. Okay? So it's going to equilibrate with what's inside the cell. And inside the cell at rest is a PO2 of 40, and that venous blood goes back to the heart, goes back to the lungs. We start all over again here with a PO2 of 40. Okay. Now if we look at the CO2, now we're looking at the CO2. In the arterial blood, we have a PCO2 of 40, and you know that CO2 is going to move out of the cell and into the blood. Okay, and therefore, the PCO2 must be higher in the cell than it is in the blood. So the PCO2 in the cell must be higher than 40. Okay, and what we see is that the PCO2 in the cells at rest is about 46. Okay? And in that arterial blood, it's 40. So we're going to have CO2 moving from the cells actually into the blood. Okay? And we have a gradient of 6 because 46 minus 40 is 6. So we have a gradient of 6 driving CO2 out of the cells, okay, and therefore, and it's going to equilibrate with what's going on in the cell, which is 46, and therefore we're left with a PCO2 in the venous blood of 46, okay, and that PCO2 is going to be carried, or I should say the CO2, with a pressure of 46 is going to be carried in the venous blood back to the heart, right atrium, right ventricle, to the pulmonary vein, into the lungs. And again, what we see coming into the lungs is a PCO2 of 46. Okay? So let's summarize this. Alright, so again we're going with 105 here. Pretend like it never said 100. Okay? So in the alveoli we have a PO2 of 105, a PCO2 of 40. In the venous blood we have a PO2 of 40, a PCO2 of 46. Okay? And so you can see that this is going to favor oxygen moving into the blood because the PO2 is higher in the alveoli, and it's going to favor CO2 moving out of the blood into the alveoli because the PCO2 is higher here in this venous blood than it was in the alveoli. It's all going to equilibrate with what's in the alveoli, which is 105 and 40. Okay, 105 and 40, 105 and 40. That blood is going to continue through the system. It's going to end up in our cells. We still have 105 and 40. At rest, what we see in the cell is a PO2 of 40 and a PCO2 of 46. Okay, that is going to favor oxygen coming into the cell because this PO2 out here is higher than the PO2 in the cell, and it's going to equilibrate with what's in the cell, which is 40. And we're going to see CO2 leave the cell and go into the blood because the PCO2 in the cell is higher than the PCO2 in the blood, and that's going to equilibrate with what's in the cell, which is 46, and that's going to go back and start all over again with 40 and 46.